Hello, thank you for studying math with me and watching this video. I would like to open with a little bit of positioning and context. We have talked about solving differential equations and some mathematical modeling in Chapter 1, Chapter 3, and also in Chapter 8 a little bit about systems of first order differential equations in the last one. But what we haven't done much of is modeling second order differential equations, although we have solved a number of them. So this really will be addressing elements of Chapter 5. It will lead to a take-home problem where you're going to be doing some modeling and solving a second-order differential equation. Now the concepts from this lecture will probably be useful, although they won't be identical to the problems that I will talk about here, but I will think that this will be a good review of other solution techniques as well. So as you watch this, I'm going to suggest that you remember that math is more than a spectator sport, so having pencil and paper in hand and using these buttons will be useful as you prepare and learn from these videos. And what we're going to be discussing is mechanical vibrations, but these are very generalizable to other systems, and we'll talk about at least one significant example of that. So here's the model that we're going to be working with primarily. And it's going to be a model of a spring, which you may have studied in some of your engineering or physics courses. The first thing I would like to observe is that the coordinate system that we're choosing to have is going to have x being greater than 0 when you go down, and it's going to be negative when you're going up, and then this corresponds more or less to the length of the spring. And there is a point in the middle which is called x equals 0. I'll talk more about that. So we have a spring which has a rigid support and is unstretched in this first picture, and that length is called L in this diagram. What we do is we hang a mass on this spring, and that pulls the spring down further than L, down to a place called, well, it's going to be L plus S. This distance is going to be S, and that is going to be called the equilibrium position for the mass. And at that equilibrium position, the force down, which is going to be the mass times the acceleration due to gravity, m times g, is exactly balanced by Hooke's law for springs, which says we have a spring constant times the distance that the spring is moved from its resting point, which was over there. And these two are exactly balanced because the mass is not moving, and that means that mg is equal to minus ks, where k is the spring constant. And now what will happen is that will correspond, this equilibrium position will correspond to x equals 0. So the concept is that we pull the spring down with a mass and we will release it, or we perhaps shove the spring up and we release it, but the spring will start going up and down, and that's the vibration that we're going to be studying. And going forward, it is important that you realize that that is identically equal to 0. And what we will be calling this is simple harmonic motion, and we're going to be talking about this being free from external driving forces and also undamped, that we're assuming that this is a frictionless situation, that there is no resistance to the motion. So now what we will do is look at Newton's second law. So this is the net force, m times a, but a is the second derivative of the position with respect to time, is equal to, this is the force associated with the gravity, and this is the force associated with Hooke's law, so that is the net force. And so depending on the position that we pick and add it to that, there will be a net force that will happen, and that's what's going to be driving the action. Now, but this part was equal to 0, so that means that we really have ma is equal to minus kx. And so what we're going to happen then is this is going to be 0, so we end up with the second derivative with respect to t of x is going to be constant, and this is going to be a positive constant because we move it to the other side, and so that's going to be omega squared x, and omega squared is equal to k over m. And so we have a very familiar differential equation here. This is d squared plus omega squared operating on a function x. is equal to 0. We know that that has a solution of x of t is equal to c1 cosine omega t plus c2 sine omega t. And we can have initial conditions associated with this. The period is the amount of time it takes to make to complete one cycle, and that's going to be in this case time, and it's 2 pi over omega. There's a quantity called the frequency, which is the reciprocal of the period, that is cycles per second, and that is going to be omega over 2 pi. And there is, in fact, a fundamental frequency that is associated with the system itself, depending on the spring constant and the mass. So we will have solutions that look like this to this fundamental equation. Now, when we have a constant here and another constant here, and we have a sine and cosine, we're not really clear what the amplitude is. So engineers often will consider a use of a trig identity where they will change that signal into being a sine omega t plus phi, where phi is called a phase angle and a is the amplitude, or x of t is equal to a cosine omega t minus phi. These are derived with trig identities, but from an operational point of view, you can say that the amplitude is going to be the square root of c1 squared plus c2 squared, and the angle phi can be found by computing the tangent of the ratio of the sine phi to the cosine of phi, and these are associated with the initial values in terms of the cosine being c1 over the amplitude and the sine being c2 over the amplitude, and then the tangent of phi is c2 over c1. We'll do some examples of this later, and in fact, the examples will begin right now. So this first example we talk about is a 16-pound object stretches a spring 8/9 feet by itself. Notice that this is happening in the English system of measurements, because we're talking about feet and pounds. There is no damping and no external forces acting on the system. The spring is initially displaced 6 inches, note that that says inches, not feet, upwards from its equilibrium position, and is given an initial velocity of 1 foot per second downward. Find the displacement at any time t, and we're going to call this u of t. So here's how we proceed with a solution to this problem. First of all, we're going to have to find the mass, because the mass was involved in our equation we had earlier. So it's going to be 16 pounds divided by the acceleration of gravity, which I'm taking to be 32. That makes the mass equal to 1/2, and the units of that are called a slug. We also will use the fact that we have mg is equal to ks in the equilibrium position, so that means mg is going to be the 16 divided by the displacement that happens because of the weight, which is 8/9. I do that arithmetic, and I know what k is, so the spring constant is 18. So I will write my differential equation as we had. This is 1/2 u double prime plus, this is 18, u is equal to 0. That means u double prime plus 36 u is equal to 0. And here are the initial conditions, and notice I'm adhering to the convention that down is a positive and up is a negative, and I'm changing that 6 inches to feet. So my solution to this, as you know very well from this being d squared plus 36 operating on u is equal to 0, is going to be c1 cosine 6t plus c2 sine 6t. And when I plug in the initial conditions and work through it, I get these are my values. Now I am going to, on this one, change this into the other form. So the amplitude is found by taking the square sum of the two coefficients, squaring each of them, taking the square root, that is root 10 over 6, and then we are going to be pretending to be engineers today, and so that is going to be that via a calculator approach. And then phi is going to be the arctangent of 1/6 divided by negative 1/2, which is approximately this number. Now it is important that students realize that there are two values that will have a tangent that is a negative, and that will be in the 4th quadrant or in the 2nd quadrant, and you have to think about which one of these is the appropriate one for this configuration. Well, if we go back and look at what C1 was, C1 is the number that's being multiplied by the cosine, and so that is A, and that whole coefficient C1 is A cosine phi, and that means, since the amplitude is always a positive number, that means that the cosine is negative, and similarly C2 is A sine of phi. That means that the sine is positive, so the only place where that happens is the cosine being negative and the sine positive is in the second quadrant. And so what we're taking as our value is not that one, which our calculator gave us, but rather that one. And so our solution is u of t equals, there's our amplitude, that is cosine 6t minus that number in radians. Now, if we were to graph that, this is what we get. And you can see that the amplitude is just a shade over a half. It goes up and down, and it has the period and frequency that we had, and it never dies out because we were assuming that there was no resistance. Now, this ends the first of several videos that we're going to look at, but make sure you feel good about this one before going on to the next one. Take care, and I'll see you in the next video.